Joey Armandi, who's going to be talking about combining gradual typing and dependent types and a new approach to solving that problem.
All right. So this is joint work with Eric Tonterre and Ron Garcia. So first off, the kind of bullet point summary, what did we contribute? We created GDTL, which is a gradual dependently typed language. So it supports full spectrum dependent types. There's types and terms are interchangeable with the universe hierarchy. But the key is that you can replace any type or any term with question mark, the unknown value. And it embeds fully a dependently typed calculus, but you can go all the way down to an untyped calculus and anything in between. And the key, and really the key contribution of our paper, is we showed how to keep decidable type checking when you have this sort of system. So that's what I'm going to talk about in this talk. We also have a proof of gradual type safety, and we support the gradual guarantees so that you can smoothly transition between various levels of typedness, and if you're interested in that, see the paper. But why do we want gradual dependent types? Why should we care? And so dependent types have a lot of potential when it comes to reducing errors in programs. But while we'd really like to have dependent types just get rid of our bugs and tell us how to fix them, the reality is that we often the reality is that we often spend a lot of time fighting with the compiler and trying to convince it that things that are correct are in fact correct. And so dependent types have become popular for proof assistance, but in the big picture, they're not popular as programming languages. They're not displacing C and Java. And this is really what we'd like to focus on, is dependently typed programming. And so we see this kind of vicious cycle happen, that there is some inherent complexity to dependent types. And because of this, there's a bit of a high barrier to entry. And because of that barrier, there aren't a lot of people who use dependent types, which means that there isn't a lot of tooling and the ecosystem isn't really developed, which of course raises the barrier to entry, and we see this cycle. And so we want to help at least reduce this cycle. And if we have the flexibility of gradual typing, we think this will help for rapid prototyping and getting started with dependent types. And also, the ecosystem will grow faster if it's easier to port from other languages and easier to interface with other languages. So what should a gradual dependently typed language look like? And so, for example, we'll start with the hello world of dependent types, which is lists versus vectors. So in kind of the Haskell or ML version of lists, we don't have any knowledge about the size of the list in its type. And so if we have a function like head, this is a partial function. If you give it an empty list, it will raise an error. Whereas the dependently typed version of this says that we are going to keep the length of the list or of the vector as an index. So now it depends on this value. And our head function becomes total because we restrict its domain to be only non-empty lists. And so if you try to give this nil, it won't even type check. Now imagine that you're not an experienced type theorist, and we're porting code from Haskell or ML or a language like that, and we want to switch it something that was using lists to something that is using vectors. So for example, we'll use a quick sort. So takes in a list of integers, outputs a list of integers. Sorting the empty list is empty, and if sorting a non-empty list, you take everything less than the head, sort that, put the head, and then sort everything that's greater than the head. And so this relies on our filter function, which just gets everything in the list that fulfills a certain predicate. Now imagine that we wanted to do a straightforward porting of this from a Haskell-like language to a dependently typed language. So we're going to change our type signatures. We're going to say, okay, well, what we had list before, we have vectors, and there's some integer n, or some natural number n, that's the length of our list. And for our empty case, this is good. Nil works just as well as a vector as for a list. But we're going to have two problems when we have the case for non-empty list. First off, we need a proof that these three lists, when we concatenate them, that gives us something that's the same length as our original list. And don't get me wrong, you can do that proof, but you have to do the proof yourself. But the second thing that's even harder is that our filter function, well, when we're porting it, we know that it takes in a vector of length n, but we don't know statically what its return type should be because we don't know how many elements of that list are going to fulfill our predicate. So how do we solve this? And again, this is not an unsolvable problem for static dependent types. You say, okay, well, there exists some number that this is the number that the predicate fulfills, and you would write a proof that looks something like this, where you take in a vector and your predicate, and then you show that, okay, you give me a vector of the length of the result of taking all these filters and adding them together, and I can give you a vector that's the correct length you're looking for. And so you can do this, but you need to do an inductive proof. You need to know about the commutativity of addition, and it's not something that is, it's going to be a barrier when you're trying to do a line-by-line transfer of your code from one language to another. And so when we do this, we could just, once we have this proof, we can just wrap our sort in this and everything will be well and good, but there's significant effort required for this. So how about gradual types? They're a tool in our toolkit. When we want them to be want something to be flexible, we introduce some graduality. But the problem is that filter, we could make it return unknown, this unknown type. But now we can have filter accidentally return something that isn't a list. It could return 3 or true because this unknown isn't specific enough to tell us that we want a list, but we don't know what its length is. And so this is where gradual dependent types come in. What we want is for filter to return a vector of integers with unknown length. And so this is then precise in the type. We know that whatever we get back is going to be a list, but it's flexible in the length. And so this is the approach that we advocate and the approach that GDTL uses. So going back to our sort example, it's very easy to do in our language. We just say, well, filter will return something of unknown length. And then when we do this length computation for concatenating the lists, we have unknown plus 1 plus unknown, which is itself an unknown value, which is critically consistent with our target type length of n. And so the key is that it's then inserting these dynamic checks to make sure that when you actually run this program, you're not violating the type guarantees. And so let's look at some examples of how these things will behave. So if we've got our head function, and then let's say we start with a vector that we statically know is empty. If we try to call head on this in our language or in any dependently typed language, this shouldn't type check. If instead we change it so that we don't statically know the length of our vector, we say we will give it the unknown length, then this call type checks because n plus 1 is consistent with unknown. And then how it behaves at runtime depends on what we instantiate it with. If we instantiate it with an empty list, then this is going to give us a runtime error because it's going to say, I expected n plus 1, but you gave me 0, and those aren't compatible. And then if you instantiate it with a non-empty list, then it's going to do that check, but of course it's going to succeed. And so we get the safety, but these checks are transported from compile time to runtime. Now, we've seen that you can use the unknown as a value as a type index, but it turns out that there are also proof terms in dependently typed languages, which don't really change the behavior of the program, but exist really to convince the type system that your program is doing what you want it to be doing. And so let's imagine that, okay, we don't want to leave filter as having unknown length. We want to go back and actually fill in that proof term. And do it the hard way, but we want to do that eventually. So if you've coded in Idris or Agda, you write out your type signature, and then you say, well, I want to fill this in later, so I'll leave a hole there. And we're going to do something similar. We're going to leave unknown in place of the proof term. And so this is like a hole in Idris or Agda. And then we can wrap this in that proof to show it. But the key is that in our language, this code type checks and you can run it. So even before you finished proving, convincing the compiler that you have all the type information you need, you can test out your code, you can get a sense of its behavior, you can have a REPL running with it, because we've given a dynamic semantics to unknown. So specifically, unknown has the unknown type, which means you can use it as a value of any type. And if you ever eliminate it, you get unknown as a result. So if you function call or if you pattern match on it. And then we insert these runtime checks to ensure that whatever type guarantees the proof you were using unknown in place of, it ensures that those type guarantees are in fact enforced. So if you try to do something crazy, like have a proof of 0 equals 1 that you leave as unknown, and then try to use that to substitute 0 for 1, this is going to type check, but it will return a runtime error because it'll be able to see at runtime that 0 and 1 are not in fact the same thing. And importantly, it's not going to seg fault or access bad memory or launch the missiles. Let's look a little bit more at the details of GDTL. So in terms of the statics and dynamics, we drew mostly from abstracting gradual typing, which is, if you haven't seen it, it's a framework to systematically take a statically typed language and turn it into a gradually typed one and give strong meaning to what those gradual types mean. But this didn't fully work with dependent types, and so we had to extend it in a few ways. And so the main one was because of this type term overlap, where before we only had gradual types, now we have gradual types and terms. Specifically, we can use unknown both as an unknown type and as an unknown term. And so this means that now where we have type indices, we can have an unknown value for our type index, and where we have proof terms, we can say that there is an unknown value for that proof term and that we can still run those programs. They can still be full working programs. Now what's the catch? What's the problem? And with dependent types, we have to evaluate terms at compile time. And this usually works because they're strongly normalizing and they don't tend to fail. And this has an inherent conflict with gradual types because evaluating gradual types introduces these effects. Specifically, we can diverge because now you can give a type to self-application, or you can have errors, and these errors are a key part of gradual typing. They're what makes it safe. And so how do we remedy these two supposedly conflicting things? And the key idea is approximate normalization. So we exploit the phase distinction between compile time and runtime. And we're going to say when we normalize terms at compile time, we're going to make sure this always terminates, and we're going to do it by only giving approximate results, which means that sometimes we will give unknown as the result of normalization when we don't have the type information to ensure that it's safe. Whereas at runtime, when you actually run your programs, we're going to say, okay, we'll allow that to diverge, we'll allow it to fail, but we're going to give exact results. We're not going to ever error out and say, I give up, unless you encounter a runtime type error, but that's a different class. So where do we approximate? And so the first one is for termination. And so we base this on hereditary substitution, which, if you haven't seen that before, it's a way of structuring normalization where there's a nice structural argument for why it's decreasing and why it's terminating. And so we adapt that and we say, we just manually inspect that. We say, are the types structurally decreasing as we evaluate? And if they are, then this is good. We can safely proceed knowing we're working towards termination. And if we ever hit a point where they're not decreasing, then we approximate and we say we have to return unknown. So if we have some crazy term that evaluates and eventually it gets to something with that's going to loop forever, when we look at the types of this, we can see that, okay, X is what we're substituting for. It starts off with a type, and then as we evaluate it, the types get smaller and smaller until we hit the point where they don't, because we are using this gradual type to treat question mark like question mark to question mark. And that's where we approximate and say, I can't proceed safely, I give up. The second approximation we have to make is with downcast, and this accounts for these type errors, which is our types are ordered by precision. And it's always safe to lose information. We can say, well, I know this is an integer, but I'll forget that it's an integer, treat it as unknown. But we can't go the other way around. If something has unknown type, we can't necessarily treat it as an integer. And so anytime at compile time, when we're moving downwards in this precision direction, we approximate. So for example, if we have 3 and we're converting it from a nat to a bool by going through the unknown type, we succeed when we go from nat to unknown, but we have to approximate when we go from unknown to bool because we don't know that that will succeed. In terms of the runtime semantics, this is more straightforward. We use the AGT notion of evidence, which is basically we just keep the most precise information about each value that we know, and then we combine it using a meet operation. And we'll raise a runtime type error if we ever if this meet ever doesn't exist. So to sum up what we've seen so far. So we built GDTL, which is a full dependently typed language. You can add imprecision anywhere in your program where you want. We are fully typed, but you can also go all the way to fully untyped. And the thing that makes it all work is approximate normalization. There's still a few things to work on. We're figuring out inductives because they don't play nicely with hereditary substitution. And then, of course, if our goal is to make dependent types easier to use, we want good error messages, and we want decent type inference. And so our eventual goal is we'd like to make a fully gradual front end to IDRIS. So that's GDTL. I'm happy to answer any questions. Thank you.
So first question from online. Type indices are often considered computationally irrelevant. We want to erase them at compile time, but it seems like with the gradual typing, you can't do that kind of type erasure. So how do you reconcile that?
That's, I mean, in general, that's a difficulty with gradual typing overall, is that you necessarily need to keep some type information at runtime that you otherwise would have erased. And if we've seen it, some of the past work in that it ends up being a significant performance problem. So unfortunately for right now, the answer is that it means that things that could be erased before now can't be. But it's, I mean, A, helping with that is future research, and B, it's eliminating an optimization, but the programs will still behave in the way they did before modulo runtime.
You have up here.
So I've been saying for years that it would be a good idea to have gradually type-dependent languages to lower the barrier to entry. So I completely agree with what you're saying there.
Thank you.
That's fantastic. There are lots of details to be filled in here.
Yes.
Am I right in thinking that you're looking more at, say, IDRIS than AGDA, in that you want dependently typed programs rather than proofs of them? Because you could always write question mark as your proof, so that'd be very questionable.
Yes, that's definitely the case. That yeah, we're targeting more, like, this isn't a full-blown gradual type theory. We're definitely targeting the programming angle more. But
sorry, by more, I want to be specific here.
Yes.
As far as I can tell, you can't do proofs here, because you could always give question mark as your proof, and you'd prove anything.
So you can prove anything, but if you ever try to use those proofs, so like if you never intend to run your programs, then this is not the language for you. But if you intend to run your programs and prove things about them for the sake of safety, then you can still do that, because even if you have question mark as your proof, it's going to insert the runtime check to make sure that you're not abusing that proof. And yes, the goal is that when you, for example, if you're releasing a product, you don't want to have a bunch of proof terms omitted, but it lets you still run your program in that intermediate stage.
Right, as long as you don't depend on the proof. So in the example of sorting, like you said, you could run this.
Yes.
Yeah, but you included this function whose definition was question mark, which was supposed to be the identity. So at that point, you could run your sort, but it would fall over. It wouldn't actually sort.
Right, but you can, like I had been trying to come up with a kind of minimal example, but there are ways where you can run it, and it will actually do the check and say, okay, now I know to check if this list is empty or not, or to check that the lengths actually line up. And there you can run it, and it will run to completion if you've fulfilled all your type guarantees, and it'll throw a runtime error if it doesn't.
Okay, and then
sorry, let's move on to another question, and you can talk offline. Okay. Can we over there?
Hello, thank you. That was good. I liked it. Actually, I understood it. That was good about it. And the question is, can I have, for example, a function that takes a Boolean and returns this question mark, and then I do a pattern match. If I get a true, then I return like string value, and if I get a false, I return an int value. As I'm guessing, this will type check because the question mark accepts everything. And then if I use this function in my code that way, that I never get a typer, like in my understanding. When I expect string, I always get a string from this function. When I expect int, I always get an int from this function. This will work, am I right?
Yes, that will work. It's not just like Haskell types to dependent types. You can do full dynamic dynamic typing with that. But if you ever call that function and it gives you a string and you try to use it as an int, then it will have the error. But as long as you don't, as long as you only use it where it's actually expecting a string, then it won't ever error out.
Okay, thank you. I understood even more.
So I have another question from online about blame tracking, and is it possible to find the sources of unexpected question marks at compile time?
Probably. That sounds like excellent future work.
So over here.
So you explained that your type checking time semantics sometimes reduces things to question mark. So that seems dangerous to me because it's going to make things equal that weren't actually equal to start with. So does that mean that, for example, do you have an identity type, and is there some kind of interaction there somehow, or?
Yeah, so it makes things equal that weren't otherwise equal, but only when you haven't provided enough type information for it to do it. So for example, if you had some dynamically typed computation that's computing the length of a list, then that's where it introduces some danger, because now it's going to say, well, I couldn't actually do this computation, so this list has length unknown. But it still is safe in the sense that that check exists, but it's moved to runtime. And then the other side is that if you have used, if you've provided enough type information, then it will still, it won't approximate. But that kind of making things equal that weren't is necessary to preserve the gradual guarantee. So it's a trade-off for whether we want to support the smooth transition versus whether we want to be a little more guarded about what could and couldn't fail. Have a what? Not
The question, sorry, the question was, do you have an identity type?
Yeah, we have not an inductive identity type, but like we baked it into our prototype, and yeah, it basically works by if you have two things that aren't actually equal at runtime, when you eliminate on the proof of reflexivity, it will actually compare those two things, and if they're incompatible, then it will throw an error. But figuring out the kind of more advanced types is definitely something we're looking at.
Okay, so let's thank the speaker again, and we have a break.